Welcome back, guys. I'm going to start introducing you guys to two-dimensional motion. But before we do, I thought we would go over a one-dimensional motion problem that's a little bit more complicated. In this one, we have two objects moving towards each other. We have a train leaving New York traveling at 56 miles per hour and a train leaving Cleveland traveling at 45 miles per hour. If the track distance between Cleveland and New York City is 520 miles, when and where will they collide? So I know that New York is located here. I know Cleveland is located here. I'm saying that this is 520 miles. The thing that's going to be the same for the two of these is the time. So they'll have the same time. So I'm going to have my New York train. I'm going to have my Cleveland train. Either one of them has acceleration, and I'm going to make the distance that the New York train travels x. So that means that the distance that the Cleveland train will travel will be 520 minus x, because x plus 520 minus x is equal to 520, and that's the total distance. So this is going to be x, this is going to be t, this is going to be 520 minus x, and this is going to be t. So I'm going to have a couple of different equations, but they're going to have the same variables. So for the New York train, x minus x naught equals v naught t. So that means that x is going to be equal to 56 times t. For the Cleveland train, x minus x naught is also going to be equal to v naught t. And in this case, it's going to be 520 minus x is equal to 45t. So I would be able to solve for x or t and substitute it in to the more complicated equation, or I could add the two equations together. So if I add the two equations together, if I put this one below it, I have 520 minus x plus x is 520, and that's going to be equal to 56t plus 45t, which is going to be 101t. And so t is going to be 520 divided by 101. Again, this is going to give me an answer in hours. So I get 5.15 hours. Then I can plug it back into the original one to find out what the distance is. So x is 56 miles per hour. And it's going to go for 5.15 hours. So 288.54 miles from New York they would meet after 5 hours. All right, so the next section is going to be projectile motion. And this is going to be very much like free fall. If you remember, free fall was something that was moving in one dimension, only under the effect of gravity. This is going to be something moving in two dimensions under the effect of gravity. So that means there's going to be no air resistance. Everything that is a projectile follows a parabolic path. Many things can be projectiles for us. So if we're thinking about a baseball or a cannonball or a pinball, like I did in the demos, which hopefully you've watched before this video, or a cart falling off a table, most things we can ignore air resistance for, especially round things. You saw that for the most part, they have to fall real far distances for air resistance to matter. Okay, so the big thing here is that gravity acts down. So our acceleration is this little g, and we're saying that it's near 10 meters per second squared. So that means that this acceleration only affects your vertical velocities. So if I look at what's going on, and in this section, we're only going to look at horizontal launch. AP really loves horizontal launch. We'll look at two-dimensional projectile motion at another time. So in this case, we have horizontal launch. It has only velocity in the x direction. My velocity in the y direction starts off being 0. So something's rolling off a table, something's being shot sideways. As time goes on, this arrow keeps the same length. In the x direction, there is no acceleration. So that arrow is not going to shrink or get longer. It's going to stay the same throughout. Which again, hopefully you've seen those demos, and I demonstrated that in a couple of different ways. In the y direction, because you have an acceleration, your velocity is going to go from being 0 to growing, to growing, to growing. This arrow is the combination of the two of them, the one that's at the angle. So because we have acceleration only in one of the dimensions, and all of these problems will consider the x direction and the y direction independently. And we'll have two different charts. It's the same problems we had, because we're still saying we have constant acceleration. And we'll realize that the thing that'll be the same in both the charts will be the time. All right, so as a demonstration, I want you to watch this short video, and it shows how horizontal velocity remains constant.
So here's the golf ball. I'm going to fire the gun now. Close. Close. Reasonably close. Well, since it's only reasonably close, perhaps it would help if we give it a little bit of leeway. There goes the gun. Here comes the ball. This is just in case. down. As I'm going to push this now, give it a push, the gun will be triggered when the middle of the car is here. You've seen how high that ball goes, so that ball will go. And depending upon how hard I push it, they may meet here or they may meet there. You ready for this? You ready? I'm ready. Physics works. See you Wednesday.
Okay, so that was Walter Lewin, who is a physics professor or was a physics professor at MIT, and that's a freshman level physics course at MIT. All right, so the horizontal velocity remains constant. Even when he shot it, and hopefully you've seen my video as well, it had the same horizontal velocity as the cart. It didn't matter that it became a projectile. That horizontal velocity was the same, and so it landed in the same place. Now, why did he need the cone? It's possible that that cart would have slowed down slightly because there is some friction, and so that helped make the demonstration work a little bit better. So, gravity is always perpendicular to that velocity, and because of this, it can't speed it up or slow it down. It can only change its direction. All right, so here is a stop motion picture, and it's taking so many pictures per second of something being dropped and being shot. And I did this as a demo for you guys, and you could see that the distance that it traverses in the Y direction is exactly the same, whether it's shot sideways or if it's dropped. And it's getting bigger and bigger. That tells me that the velocity in that direction is growing and growing. Move this out of the way. But the distance that it's going in this direction should be the same. So from there to there, where this one's located, should be the same as from there to there. Besides the initial one here, when it gets to, this one's bigger because that's when it got pushed. And I did this for you. That was the one where I was standing on the table. If you're launching at an angle, the only thing different is that you have a velocity in the Y direction to start with. And so we would look at the components. This dark green arrow is our actual velocity. This is our component Vy naught and Vx naught, and these two together would make up that one. This would be the resultant of those two. So these would be the components. And you can see as it's going up, since acceleration is down, it's causing this part of the velocity to shrink. And then there's a moment at the top where it doesn't have any velocity in the Y direction. So that's the moment when it's at its peak. This half, if we just consider that half, is the horizontal launch half. And you can see that the magnitude of the initial velocity, how long this arrow is the same as the magnitude of our final velocity, how long that arrow is. Now, they're not directed the same, but they're equal. And these two halves are the same. They're two halves of the same parabola. So again, looking at our arrows, we can see the red arrow is shrinking, where the blue arrow is the same length everywhere. And again, these are components. The actual velocity would be the combination of the two of these at any given point. All right, so to solve these problems, the big step is to have two charts. So we're going to have an X direction chart and a Y direction chart. And again, our equations will be the same because our equations work for a constant acceleration. And gravity is constant acceleration, and then in the X direction, 0 is constant acceleration. So in the X direction, your initial and your final velocities are always the same because you have no acceleration. In the y direction, your acceleration is always negative 10. Unless you're off Earth, which there will be problems on the moon and such. So at the peak, at the highest point, your velocity in the y direction ends up being 0 momentarily. And for both of our charts, they're going to share the same time because we're really talking about the total velocity. All right, so a couple more videos just to hammer this home. You saw where I launched something and dropped something. The very famous example was shooting a cannon and dropping a cannonball. The more modern example was shooting a bullet and dropping a bullet. So in this video clip, you're going to see them shoot a bullet and drop a bullet. And what they did was they dropped a bullet where the bullet they shot was going to land. Because obviously if you shoot a bullet and drop a bullet from the same place where they actually hit the ground at the same time, they're far apart. So what they did was when they shot the gun, they made a device that dropped the bullet where it was going to land and then wanted to see whether a bullet launched just horizontally with no vertical velocity hit at the same time or not.
Everything's hot. Let's do it. And after a few test fires and a bit of fine tuning, it works. Oh, it's good. It's good. It's 1/3 of a millisecond difference. Wow. That's freaking perfect. Let's go do this full scale. Okay. Which means rolling up the room 360 feet to stake out a drop zone. Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here. Okay. Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history. All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed. Let's go see where it hit. So Adam takes a one-wheeled ride down the room to check out the drop zone. Wow. And the results are simply ripping. Can't get much closer than that. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for. In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers. 3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics. Was needed.
And then finally, this is the last demonstration I did for you guys.
We've been using some little bitty cannons. I think it's time we need to get out the big stuff, don't y'all? How about this one? Now, for this demonstration, we know that gravity acts on everything, whether it's moving or not. So I'm going to shoot this cannon at Hank when he's at the top of the gantry. But if I do that, as soon as the cannonball leaves the end of the barrel, gravity's going to start pulling it down. And if Hank's lucky, it'll miss him. It'll go underneath him. So how can we make sure that that doesn't happen and I get to hit Hank? The way we're going to do it is at the moment the cannonball leaves the end of the barrel, we're going to drop Hank. I like this one. Now, to make sure that happens, we have a magnet that's powered by the cannon that, you ready, Hank? No. It's held in place. And I said that whenever the projectile, the cannonball, left the end of the barrel, it was going to drop him, and this is what's going to happen. When it leaves the end of the barrel, there's a switch that drops him. So, that's what we're going to do. So, we're going to put this thing back together. Ready, Hank? Yes. Power's on. And to make sure that this is pointed right at Hank, I have a laser that I'm going to have in the end of the barrel, and we're going to shine it right on his baseball glove. And then we know it's pointing straight at him. Okay? And away he goes. Good. A little more. It's hang on. Okay, that's fine. Okay, Hank, can y'all see the laser beam on the back of his glove? Okay, so now we know it's pointed right at him, right? So I'm going to remove the laser pointer. That's out. And the first time I fire the cannon, we're not going to drop it so that you can see what the cannonball looks like as it's flying across the stage, okay? Now, here we go.
If I don't drop, he can't hit me. Because gravity will bend the bullet away from me.
Count to three. 1, 2, 3. Okay?
Now, the next time he fires it, I'm going to fall. And the bend of the bullet and how much I fall are going to match, so I get to catch the ball. Now, let's say he shoots it faster this next time. If he shoots the bullet really fast, it gets here so quick that I don't fall very far, but it doesn't bend very much. So I just catch it down here a little bit. If he shoots it slow, it takes a long time to get here. I fall a long ways, but it bends a lot, so I catch it down there by the bat. If gravity didn't even work, I wouldn't fall and the ball wouldn't bend. I'd catch it right here. Nothing can go wrong with this demonstration.
Say, Hank, before I shoot the cannon, do you remember the comment you made about my brains coming out of the back of my head? I'd like you to think about that in your life classes. I'm going to arm it.
Yes.
Ready? It's armed. Okay, a little help. On the count of 3. 1, 2, 3.
All right, so just like I did with my Monkey and the Hunter, we could see that whether something's dropped or shot, that gravity affects it in the vertical direction in the same manner, because they're both being affected just by that acceleration due to gravity. When we come back, I'll show you how to do projectile motion problems.